everybody. So today I'm going to talk to you about Le Chatelier's principle. And let me define it for you first so that you have an idea of what it is that we're talking about. So at this point, we've gotten the system to equilibrium. And now what Le Chatelier's principle talks about is what would happen if that system's equilibrium was disturbed. So what would happen if we put a stress on the system? And so the definition of Le Chatelier's principle says that when a stress is applied to a system, the system will react to counter that stress. So they call this reaction where the system will actually, try and counter the stress, a shift. So when we talk about a shift, that's how the system will react to the stress to counter it. Well, what are the three stresses? Well, we could have temperature as a stress. We could have concentration as a stress. And we can also have pressure as a stress if there's gases. So those are our three stresses. And what we can do with each of these, for temperature we can either increase it or decrease it. With concentration we can either increase or decrease either the reactants or the products. And with pressure we can either increase it or decrease it. And we can do that by changing the volume of the container. So I wrote temperature first. So let's start with temperature, and I'm actually going to zoom in here so that I can write more for you in a short amount of, or a small amount of space. So let's increase the temperature first. So if we increase temperature, what will happen is that both the forward and the reverse reactions will speed up. Whenever you increase temperature, it's important to understand that the reactions speed up, regardless of if we're talking about the forward reaction or the reverse reaction. But the thing with increasing temperature is that the endothermic reaction, the reaction that uses an increase in heat, will speed up more. And so what we're doing is we're basically favoring the endothermic reaction. So for example, if I were to put a reaction up top here, if I were to put something like A goes to B plus heat, if I were to stress out the system by increasing the temperature, I'm essentially adding heat to the system. So the stress is to add heat to the system. How does the system react? Well, it favors the endothermic reaction. So in this case, it's going to favor the reverse reaction. Now, what does that mean in terms of what happens to the system? Well, when we favor the reverse reaction, what will end up happening is the reverse reaction will be faster than the forward reaction. The concentration of A will increase as a result, and B will decrease as a result. They happen to call this a shift to the left because we're making more of the reactants, which are written on the left side of the reaction. So when we increase temperature, we're going to favor the endothermic reaction. What happens if we decrease temperature? Well, if we decrease temperature, then we favor the exothermic reaction. Now again, when we decrease temperature, both reactions decrease, the speed of them decrease, but the exothermic reaction will decrease less. So now if I were to write that same reaction, A plus B yielding heat, A yielding B plus heat, A yielding B plus heat, if I were to decrease the temperature, I'm essentially removing heat from the system. Well, how will the system react? Well, the system will react by favoring the exothermic reaction, trying to generate more heat. That means that the exothermic reaction is the reaction that's the forward reaction to the right. It will result in B increasing and A decreasing. So since I decrease the amount of heat, I sort of shift toward that side that had the heat on it. So these are the changes for temperature. If we increase the temperature, we favor the endothermic. If we decrease the temperature, we favor the exothermic. Whatever side we favor is what we make more of. So let's do concentration. If we increase concentration, this will equal an increase in collisions. This will equal an increase in the rate. And this will equal a shift away from the increase. How does this look in a reaction? Well, let's do our A to B again. So A going to B. Well, if I increase A as the stress, if this is my stress, there will be more A there. The A will react more. I will then create a reaction going forward that is faster. That will cause a shift to the right, making more B. As a result, B will increase and A will decrease from whatever was stressed out. So, like let's say that I increased A twofold, what will end up happening is I will use up some of that A that I added. Now we saw this in the lab with the chips. When we added more reactants, we used up some of those chips and we shifted towards the products. And this is the same thing here. If I look at a reaction that's a little bit more complex, let's say I have A plus B yields AB. Let's say that again I stress out the system by increasing A. Well, the result is going to be that A will collide more with B. We have more of the A around. That will cause both A and B to decrease as they get used up more, and AB will be created. Again, if I increase the concentration, I'll shift away from that increase. In this case, I increase the amount of A, so I shift away from A and I make more AB. What happens if I decrease the concentration? If I decrease the concentration, that will lead to a decrease in collisions. That will equal or result in a decrease in the rate, and that will cause a shift toward the decrease. So if we were to use our example again here, our A plus B yields AB, if I were to do something like decrease the concentration of A as my stress, now there's less A to react with B. So since there's less A to react with B, the forward rate, the rate that's making the products, actually slows down. But the reverse rate, it hasn't changed at all, at least not in first. So what ends up happening is AB, it's still breaking down and making A plus B at the same rate. However, A plus B, that reaction slowed down. They're not making AB as fast. So what ends up happening is, over time, the AB concentration will decrease. But because when you first decreased A, the AB that was breaking down, that rate didn't decrease at first, you'll get sort of a rebound effect where you get more A and more B. So again, when you decrease the concentration, that decrease in concentration causes less collisions, in this case between A and B. That slowed down the rate going forward where A plus B made AB. And as a result, the reverse rate looks like it's going faster. And that reverse rate would then cause a shift to the left and a shift toward the decrease. Now the last stress is pressure. Pressure only is for gaseous systems. If we increase the pressure, then we will favor the reaction that produces less moles of gas. So what would this look like? Well, let's say that I had a reaction with all gases, the famous Haber reaction. To find the moles of gas on each side, on the left I have 1N2 and 3H2, so I have 4 moles of gas. And on the right I have 2 moles of gas. And so what you can see is that the right side has less moles of gas. If I increase the pressure, usually by decreasing the volume, if I increase the pressure, I will shift or favor the side that has less moles of gas. So I'll shift to the right side here. In this case, it has 2 moles of gas compared to 4. The result with an increase in pressure is going to be more NH3 made and less N2 and H2. This is sort of an effort by the system to conserve space, because if you increase the pressure, a way to relieve the pressure would be to decrease the amount of moles of gas that are present. So by making less moles of gas, we're able to do that. What if we were to decrease the pressure? Well, if we were to decrease the pressure, then we would favor the reaction that produces more moles of gas. And so using the reaction above with the ammonia, the N2 plus 3H2, yielding the 2NH3, if we were to decrease the pressure, we would actually produce more N2 and H2. So these are the stresses, and I know I went a little bit quickly through this, even though this video took about 12 minutes. This is a pretty challenging part of this particular chapter. You need to really make sure that you know what happens with the stress. And what I just want to do really quickly for a minute or so is talk to you about what this looks like. In class, we'll talk more about what shifting means, just to sort of summarize what I went through in the video. I did mention it. If you want to fill this out on your own, you can, but we'll talk a little bit about it in class. But here is a reaction. This is the Haber process. So we have N2 plus 3H2 yields 2NH3. Heat is on the left side. So let's say, for example, that I were to increase N2. Well, if I increase N2, there will be more reactions and more collisions with H2. That'll cause those to get used up. Increasing a reactant on the left will shift the reaction to the right. The effect will be an increase in NH3, a decrease in H2 as it gets used up from those extra collisions, and even a decrease in N2 from where we increased it. Notice I have a dashed line through N2 because the amount of N2 will go down from the stress, but it will not go down below what originally was there. If I decrease N2, that will result in less collisions between N2 and H2. The result of that is going to be that the NH3 will still be reacting quickly or quicker, and it will get used up. The H2 will increase, and the N2 will increase from where it was originally decreased. Let's do an increase in temperature. Remember, with increase in temperature, we favor the endothermic reaction. In this case, the endothermic reaction is to the right. So increasing temperature will increase the products in this case and decrease the reactants. Let's do a decrease in pressure. A decrease in pressure, remember, we favor the side with more moles of gas. If we count on the left, we have 4 moles of gas, and on the right, we have 2 moles. So if we decrease pressure, we'll favor the side with more moles, which would be the left, and we would use up the products. So what I'd like you to do is go through and fill out the rest of this chart, and tomorrow we'll talk about what it means to shift again in case you weren't sure what was going on, and also the effects of these things on the K value. All right, thanks so much for watching.